So we are at the transport layer. We finished an overview of the TCP protocol. Let's now dig into the details. But first, a few questions. Unlike UDP, TCP is a connection-oriented protocol. In other words, a connection has to be established before you can start sending data. And during this connection establishment, both sides can exchange and initiate state variables. For example, they can negotiate what is the maximum segment size that they want to use. They can also exchange their initial sequence numbers. Why this is happening, we will look at it shortly. You can also figure out what is the acknowledgement type that you want to employ, either selective ACK or cumulative acknowledgement. Apart from this, you can also allocate resources, for example, the buffer space. So for example, once the connection establishes, both sides, the sender and the receiver, are going to allocate some buffer space for the send buffer and the receive buffer. How much is actually allocated is a function of the operating system. So these numbers can range from 4 kilobytes all the way to megabytes. In fact, you can configure these. For example, in some Linux systems, this value is 8 kilobytes. So let's look at how a connection is established. Simple. If A wants to talk with B, it can send a connection request. B is going to acknowledge this connection via a connection grant. Then both A and B can start exchanging data. Simple, right? Wrong. Things are often never so easy in networks. Remember, we are operating over a best effort service where packets can get delayed, they can get reordered, so on and so forth. So there is always the danger of duplicates from earlier showing up. So view that as a hint and tell me what can potentially go wrong in connection setup. So here is the problem. Suppose you established a TCP connection with your bank, and before the actual data, you set connection request, connection grant, and then as part of this data, you're saying transfer 20 lakhs to some account X. Now, some of these packets could have gotten delayed and the sender would have retransmitted them. And it is quite possible that these retransmissions got delayed arbitrarily, and after this connection terminated, they are again appearing at the other end. So this connection request is a duplicate that is appearing at the bank server. So in response to this bank thought it was a new connection and sent a connection grant. And here you are wondering what the hell is happening? Why am I getting some response from the bank? And in the meantime, your previous packet came and there you go, you transferred another 20 lakhs to account X and your bank balance is now nil. You definitely don't want something like this to happen. So what is the solution? It's a bit tricky, but nonetheless, think of how you can solve this problem. Originally, the TCP implementations did exactly this, but then this problem arose and later they changed the implementation. So here is the solution. The famous three-way handshake of TCP. So this idea was proposed by Tomlinson. Suppose A wants to establish a connection with B, it is going to send this initial packet. This is the initial synchronization packet, and as part of this packet, it is going to tell B that I am going to use sequence number starting from X. Now in response to this packet, B is going to set the flags SYN and ACK, where it is also synchronizing with A and saying I am going to use sequence number Y, and it is acknowledging this particular packet by saying I want X plus 1. Now A has to acknowledge this packet, so it is again going to set the ACK field, and it is acknowledging this packet by saying I want Y plus 1, and it can potentially send data as part of this connection. By the way, this is not needed. You could decide not to send data. If you are sending the data, you are going to start that particular sequence number with X plus 1. So the takeaway from this is the use of these distinct sequence numbers, that is one, and the other is that you send a packet, the other guy acknowledges, and you acknowledge the other guy's packet. So this three-way handshake is very famous, the SYN, SYNAC and ACK. In fact, there are quite a few jokes on it. Let me just tell one. It's not a great joke, but nonetheless. So a TCP packet goes to a bar and says, I want beer, please. The bartender asks, you want beer? And the TCP packet says, yes, beer, please. So this kind of captures the three-way handshake. Yeah, I know the joke isn't great, but I think you will remember the three-way handshake better given that I have said the joke. So how does this solve the problem? Let's look at it. Suppose there was an earlier transfer, and after this particular transfer, this duplicate happens to end up at the server. Now it doesn't know this is a duplicate. So it is now going to send a SYNAC and it is going to select some other sequence number. Earlier that sequence number was Y, now it has chosen Z, and it is going to acknowledge this particular sequence number. And now this other end will wonder, what is this? I've never even talked with the server again. So it is going to reset the connection while acknowledging this particular packet. So as a consequence of this, this connection will never be established. This is the more interesting case where you have both the SYN packet and this data packet duplicated. So in this particular case, let's see what happens. So again, when you receive this SYN packet, you are now going to ACK it with a new sequence number. And now the earlier connection packet has come about, and here you are confused. I send Z, why is this acknowledging Y? So something is wrong. So you are going to discard this packet and wait. In the meantime, the other end will see this packet, worry what is happening, and is going to send a reset packet, thereby aborting the connection. By the way, if this client were indeed not listening on that particular port, in other words, it closed that particular connection, in which case it is not going to send this packet. But even in this particular case, in order for the connection to complete, it needs this acknowledgement. As I said, it's a three-way handshake. It needs the third handshake from the other end, which it will never get, in which case it is going to again close the connection after waiting for some time. So let me spend a little bit more time on this initial sequence numbers. So when we were describing the sliding window protocol, we always started with a sequence number 0. Now the question is, why don't we just start with sequence number 0? It makes things a little bit less complex. As you saw here, this distinction could happen because these sequence numbers differed. So it's very important to use different sequence numbers for the different connections. So that way the segments from the different connections cannot get mixed up. Not only that, there is a security risk when using these sequence numbers that are predictable. Originally, when the TCP was being designed, this was the goal. So what they did was to use a clock to choose these initial sequence numbers. So this clock increments every 4 microseconds, and so these 32-bit sequence numbers were derived from this clock. And given that it is a 32-bit sequence number, how long will it take for the number to wrap around? Roughly 4 hours. By this time, the older packets would have definitely been removed from the network, because as I mentioned at the IP layer, these packets do have a time to live field. They are not going to live in the internet forever. But then this predictable initial sequence numbers were being used to launch security attacks. I will cover a little bit more of this as part of the quizzes. But the point to note is that this wasn't considered safe. So current implementations use random initial sequence numbers to circumvent the security threat. So this is with connection establishment. So what do you think of connection termination? You think this is easy?